pick up with Roman numeral 2, a thermodynamic view of the world. And in a thermodynamic view of the world, there is what's called the system and what's called the surroundings. And the system is that part of the world to which we are directing our attention. And more specifically, we will be interested in changes in energy, changes in heat for the system. And the surroundings are everything else. And this can get very complicated as to defining the system and the surroundings. We will generally keep it very simple, and to just be clear, or as clear as we can be, 75% of the time, more or less, the reaction is the system, and 25% of the time, the system is a material, such as a lump of aluminum or various things, solid materials, can be liquids as well. And we'll show you what this means eventually, but we're going to keep our definitions simple. Other terms that it's useful to know: a closed system is a system for which matter cannot enter or leave the system. Matter cannot enter or leave the system. And so conservation of matter is observed, and for our purposes, we will generally be dealing with a closed system where the reactants that we start with will react, but we will have the same mass rearranged for our reaction in the end. And an isolated system, for an isolated system, matter and energy cannot enter or leave the system. And there are reasons that we would be interested in using closed and isolated systems. We will not typically use an isolated system. We will typically allow our system to exchange energy with the surroundings, and then we'll define the surroundings very specifically to make sure that we know where our energy is going, in fact. Examples of system and surroundings. So the dissolving of 10 grams of ammonium nitrate in water. So we know how to write a dissolving reaction for ammonium nitrate. We would start with ammonium nitrate solid. It is a strong electrolyte, so it will dissolve and break up 100% into ions. And those ions are ammonium and nitrate. And in this case, the system is the reaction. And the surroundings are everything else, including the water in which it's dissolved. Okay. And what we will see is that when ammonium nitrate dissolves, it will exchange heat with the surroundings as it dissolves. And then that's one of the reasons we're interested in it. Now, a pen is held 2 meters above the floor. So here, this is more of a physicsy example. And here's my pen. And, well, it's not exactly 2 meters, but let's say it's 2 feet above my desk. In this case, what we'll be interested in is defining the pen as the system. So system is pen. And we'll be interested in defining the pen as a system in a physics sense, because if we know what our system is, then we can characterize, for example, its potential energy using equations that we have talked about and we will talk about. And the surroundings is everything else. Okay. Yeah. So we'll keep it relatively simple. It can get more complicated than this. Next thing we need to talk about are state functions or state properties of a system. And a state function or state property of a system is a property or function for which, or a property or function for which the a property or function that is that its changes are path independent, for which its changes are path independent. Okay, and let me see if I can make sense of that. So by path independent, I mean that the initial and final values do not depend on how you got between them. So colon, the initial and final values for the property the initial and final values of the property do not depend on the path taken. And right here I have a definition of a state function in reference to altitude. And if we look at a person going from the bottom of the mountain to the top of the mountain, you can see that altitude is a state function because altitude will vary from 0 to 10,000 feet, no matter how you go, either path B or path A or some path C. So altitude, and so let's give examples. Altitude is a state function. And now let me give a couple other examples of state functions. So the temperature in this room is, let's say, 22.0 degrees Celsius. If we turn on the heater and turn it up, and then all of a sudden we put in a lot of heat and it goes up to 30 degrees Celsius, and then it comes back down to 25 degrees Celsius, then the final temperature of 25 degrees Celsius is not dependent upon how we got there. In fact, the initial and the final temperature difference will still be 3 degrees Celsius, 3.0 degrees Celsius if we end up at 25. Now, that is a good example of something that is not a state function. Let me write down temperature. And in addition, let me write down that pressure are also state functions. And here's something that we need, delta H, which we will see in this chapter. These are also state functions. So T, P, delta H are also state functions. And counter examples, so heat and work are not state functions. And so, for example, if we come back to our example of altitude here, so you could exert a lot of work going back and forth, back and forth, back and forth as you climb the mountain. Or you could go straight up and perhaps exert less energy do less work of moving your body back and forth, and yet you would still have the same change in altitude. Altitude is a state function, but work is not. Work is not a state function. Now, internal energy is a state function. It is the sum of the potential energy and the kinetic energy for all particles in the system. Absolute values of U, the internal energy, cannot be determined. That is a complex topic that has to do with the fact that determining the energy or stored within the nucleus of an atom is currently not possible. Enough said about that. However, changes in U or delta U can be determined. There are only two ways to change delta U, the internal energy. Let me give you delta U equals Q plus W. That's the equation we're going to use. We can change the heat of the system where Q, lowercase q, is heat. And again, Q is not a state function. Q is heat, and so the amount of heat that is given off, entered into a system, is path dependent, let's say. And what we want to say right now is that when Q is less than 0, heat leaves the system. And when Q is greater than 0, heat enters the system. Okay. Now, so again, there are only two ways to change delta U. You can change the heat of the system, that's called Q. You can change the work of the system, that's called W. Work is W. And again, we will see that work, when it's less than 0, work is leaving the system. And another way of saying this is the system is doing work on the surroundings. So, or the system is doing work on the surroundings. And when W is greater than 0, work is entering the system. Or the surroundings are doing work on the system. Or the surroundings are doing work on the system. Okay, and so this idea of if you take some well-defined system, say a reaction or a pen, and then we talk about how we add heat or subtract work or subtract heat and add work, that will affect the change in the internal energy of the system, and we can keep track of that. And for me, this is something that needs examples, and the example that we need to talk about in terms of this course is pressure volume work. And in particular, what we will see is that when a gas expands, it will do work. When a gas expands, it will do work. And in fact, we will see that when gases are created in reactions, those gases will expand and do work on the surroundings. And that's where we're going to get our work from. And we will show specifically that work is not a state function, because we will take different paths between the same two endpoints. We will get different amounts of work, and yet all of our state functions will be path independent, meaning that we will start and stop at the same places, which I think is a very real way and practical way of understanding things. And we'll also relate it at least somewhat to car engines, a practical application of this process. Okay? But before we do that, So let's start by talking about what work is, and in a very physicsy sense, and I'm going to need all this space, so I'm going to start way over here. There we go. So work equals a force times a distance. Okay. And we'll call that F times D. And to go along with the conventions that we just did of work leaving a system being less than 0, we will put a minus sign in here. So work done by the system, and again we'll talk about what that means, equals the negative of force times distance. And here I've got a picture that I want to talk about this equation for work. And it goes like this. So I have a gas under an external pressure with a initial state, pressure 1, volume 1, and temperature 1. And so we can find moles if needed. And then what we do is we take off some mass, which decreases the force and decreases the pressure here, and the gas expands. Okay? And let's define some terms here. So this distance here, that's the piston here, this is a piston with some masses on it, that's going to be called delta x, where that's a triangle. And the piston area, we're just going to call A. Okay? And so what's going to happen is the area stays the same, but the piston here, when we remove the weight, it moves up by a distance delta x. Okay? Now, so the work that happens as this gas expands is going to be minus force, whatever the force is, times delta x. And we're delta, so that's our distance. And what we're going to then do is we're then going to multiply this expression on the right hand side times A over A, which is just 1. And so that's legit. And then what we're going to do is we're going to break it up a little differently. We're going to put the minus F over A together. And then we're going to times that by delta x times A. So all we're doing is we're breaking up a little differently. And what we get here is that, let's keep the minus sign, a force per area, where we know the area is just the pressure, and delta x times A, well, x times A is going to be the volume, delta x times A is going to be the change in volume of the gas. So this is just pressure, and this is just change in volume, which you can see, area times delta x, that's going to be the change in volume of the gas. And this is the relationship that we need. So the work done by an expanding gas and this is something we didn't talk about, but it's true, at constant pressure, the pressure here is the external pressure, and so when we remove the mass, it will be the pressure here, which will be pressure 2. But the work done by an expanding gas at constant pressure is equal to that pressure times the change in volume. Okay, And just because this comes up and there are two pressures, I will note, and we'll see this in the calculations, that final pressure, not the initial pressure. So the expansion is happening. We are removing this mass and allowing this to expand up at the P2. All right, well, now let's hit the examples, and we'll go back to some examples that are asking us about delta U to see how it works. It says if the burning of the fuel in a potato cannon performs 855 joules of work on the potato and produces 1422 joules of heat, what is delta U for the burning of the fuel? Okay, so delta U is going to equal heat plus work, okay? And we're talking about a system is burning of the fuel, which burning or combustion is a reaction. So the burning of the fuel performs 855 joules of work. So that means the system performs or does work on the potato, which is the surroundings. This will be minus 855 joules. And the burning produces 1422 joules of heat. That's going to be also negative. What is delta U? Well, add these up. 1422 negative minus 855 minus 2,277 joules. Oop. That is the change in the internal energy due to the burning of the fuel. Now, if a system has 30 joules of heat added to it, and hold on. Delta U equals Q plus W. If a system has 30 joules of heat added to it, good. And the total change in its internal energy is 10 joules. And the total change is 10 joules. How much work does it do? And work does it do tells us that the system is going to be doing work which is negative. We move this over to the other side. We find out that the system has done 20 joules of work, or W equals minus 20 joules. And this is the level which we're going to want to understand how heat and work affect the internal energy, or changes in the internal energy. And we need to be able to translate these word sentences, these word problems, into using this equation. Now, we're going to go to an example involving work. And for work, what we need is, and what we're going to do actually is we're going to show that the work in this case is different depending upon the path. And it says, find the amount of work done on the surroundings when 1 liter of an ideal gas, initially at a pressure of 10 atmospheres, is allowed to expand at constant temperature to 10 liters by reducing the external pressure to 1 atmosphere in a single step. That's A. And then B, reducing pressure first to 5 atmospheres and then to 1 atmosphere. And C, allowing the gas to expand into an evacuated space, so its total volume is 10 liters. So there's actually 3 calculations to do here. Looks like we're going to fit them all onto this page. And in order to do it, though, first I want to get a picture of what's happening here. So at the start, and I'll put my start up here, I have 1 liter of an ideal gas initially at a pressure of 10 atmospheres. And since this is my smallest volume, I'll draw my smallest volume there, and then I'll have pressure, and I'll call this pressure 1, or pressure initial is what I'll call it, equals 10 atmospheres. 10 atmospheres, okay? And in A, I'm going to reduce the external pressure to 1 atmosphere in a single step. So A, same piston here. Now I've got P final equals 1 atmosphere. And what I have to do to figure out my volume is I have to understand that my initial pressure and volume is equal to my final pressure and volume, because pressure and volume are state functions. So for my P initial, V initial equals P final, V final. And doing some math in my head, I can show that my final volume has to be 10 liters. And of course, my final pressure is 1 atmosphere. And these calculations work because pressure and volume are state functions. And I'll write that up here. P, V are state functions. They are path independent, as we will see. Now, to do the work for step A, and I'll note that work sub A, or process A I should call it, it's going to be equal to minus P delta V, where the P is my P final, and the delta V, well, delta V is always V final minus V initial. And let's fill in terms here. So my P final is going to be 1 atmosphere, so it's minus 1 atmosphere. My V final is 10 liters. My V initial is 1 liter. And I get, well, 10 minus 1 is 9. 9 times 1 minus is minus 9 liter atmospheres. And that is an amount of work. And we'll talk about how to convert that into joules when we have a little more space. But there is a function. So, okay. So minus 9 liter atmospheres, one-step process directly from 10 atmospheres to 1 atmosphere. Now let's do process B. And process B is going to involve 2 steps. So we'll call this B1. In step B1, you're going to reduce pressure first to 5 atmospheres. And if my pressure final here, and we'll call this pressure final B1, is 5 atmospheres, and PI VI equals P final, and for this step, V final. My V final for step B1 must be 2 liters, because P1 V1 equals P2 V2, initials and finals. So now I'll draw this as a, let's try and keep it somewhat realistic. 2 liters, 5 atmospheres. So now we can convert the, calculate the work for this step. And this is going to be the work for B1. And this is going to be my P final for B1. And then my change in volume, oh, don't forget the minus sign. My change in volume here is going to be, well, let's just call it delta V. We'll fill in the numbers. It's going to be 5 atmospheres. 2 liters minus 1 liter. And that is going to be 1 times 5 minus 5 liter atmospheres. And then we have B2, where we go to the same end point as step A. It's going to be 10 liters and 1 atmosphere. One atmosphere is P final for B2. 10 liters. Now let's do the work for B2. I know. All right, sorry, my picture is not even, I know, it's quite a process, but it's at least a relatively simple calculation as far as P times delta V. The hardest part is laying out exactly what's happening from my perspective. This time we have 1 atmosphere, and we have 10 minus 2. This time we get 8 times 1 with a negative. And now, because we started and ended in 2 steps, we're going to now add up the work. And we get minus 13 liter atmospheres. And this proves to us, hopefully, this is my goal anyway, that while pressure and volume are state functions, and we start and end at the same places, work is not a state function. Depending upon how you break the process up, you can get different amounts of work. And so note work. So different amounts of work, depending upon how you go, is because work is not a state function. So work depends on path. That's note number 1. Note number 2, so these are our system is our gas, and when our gas expands, our gas does work on the surroundings, and in fact you can see it because our gas is pushing the surroundings back. And so 2, gas is system. Gas does work on surroundings. Gas does work on surroundings. And that work is negative. And then 3, and here's the thing that has the application to engines. So in this particular system, if you break the work up into smaller steps, or sorry, if you break the process up into smaller steps, you get more work. So break process into smaller steps. The system does more work. And this gets 3 exclamation points. And what you can imagine is that these are pistons in a car, and the gas is the explosion of combustion pushing this piston back. If you have smaller pistons and more of them for the same total volume, you get more work and your car is more fuel efficient. So that's directly related to what we're talking about. If you have fewer larger pistons, then you will get less work for the same amount of process. And in the end, you will be less fuel efficient. Although in the end, if you have the same number of bigger pistons, you will get more work. It will still be less fuel efficient.